It's, I don't know, maybe it's just me, but I'll show you what I didn't like. The mean value theorem says that if you have any function at all, and you're going from point A to point B. So what I'm saying is this. We have to look at this closed interval, AB. And we have two questions about this interval. One, on the closed. Well, we draw it. Starts here. Go, 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 stop. I didn't have any problem. I had no jumps. I had no asymptotes, no vertical asymptotes. I had no breaks. It was pretty continuous. So that is good. Next question I have to ask myself before I can talk about the mean value theorem is, on the open interval, AB, only the open, I don't care about the endpoints, is it differentiable everywhere? Well, it's a smooth curve. I don't see any cusps. I don't see any sharp turns. The answer is yes. It is differentiable on the open interval. And it was continuous on the closed interval. Okay, so mean value, that I call it MVT, says this. If this is true and this is true, then there exists a secant line between those points and it has a slope. That slope has you have the same slope of a tangent line. Just pretend that you could slide this line down without turning it. Keep the same slope. Just slide it down, and what's going to happen is, lo and behold, a parallel tangent line. And guess what? The slope is the same as the tangent line, secant line. They are the same. So if it's continuous on the closed and differentiable on the open, there exists a point on this function, we'll call it x equals to c. What did I do that for? X equals to c. There is an x equals to c where the slope of the secant is equal to the slope of the tangent. That's the theory of mean value theorem. But the first page of this lesson, he's not even talking about the mean value. He's talking about something called Rolle's theorem. Rolle's theorem is a mean value theorem. There's just one little difference. In Rolle's theorem, you got your x equals to a and you got your x equals to b. The y value happens to be the exact same value for both points. So in other words, you have a comma f of a, and you have b comma, check it out, f of a. I mean, it's the same. I could say f of b, but f of b, f of a equals f of b. That's the only thing that's different. So I'm going to say the same thing. I'm going to pretend I'm doing mean value theorem. Okay, here goes. Here goes. On the closed interval, is it continuous everywhere? The answer is, from A to B, it's a solid point, solid point. Yes, it's continuous. Okay, let's look at A comma B. Is it differentiable everywhere from A to B, not counting the endpoints? Yes. Okay, then there exists a C on f of x such that y2 minus y1 over x2 minus x1. I should do that better. Let me do that better. Did Julissa get here? I didn't see her. Make sure you're all signed in on chat, guys. Let me do it better. Let me do this. F of B minus f of A over B minus A has to equal f prime at some C. Well, check this out. If f of B is equal to f of A, what is f of B minus f of A? If they're the same. What's 6 minus 6? Or 2 minus 2?
0.
0. 0 over anything is still 0. So what we're saying, that there has to be a place on this function, C, where the derivative is equal to 0. Because why? That's a horizontal line that connects f of A, and B, f of B. It connects them, it's horizontal. That slope is 0. Therefore, there's a place where the function also has a horizontal tangent. The same thing as the mean value, except this happens to be always 0. You're always looking for where it's 0. Even if you have a function that has a lot of terms in it. If I go from A to B, the Rolle's theorem says if f of A equals f of B, and it's continuous and it's differentiable, then there exists at least one C, where f prime of C is 0. Well, we hit the jackpot. We've got 1, we've got 2, we've got 3. We just need 1 to say it has to be 1, but this one happens to have 3. Okay? So I didn't like this section because he starts out talking about Rolle's theorem. Rolle's theorem is the mean value theorem, is a special mean value theorem. It's where your f prime of C is 0. That's all. That's what makes it different. So now you got to check, is f of A equal to f of B? So then he jumps to, here's the official theorem. Suppose that y is f of x is continuous at every point on the closed interval. That's the number 1. Check that. Number 2, and it's differentiable at every point on the interior. In other words, I don't care about the endpoints. This one I do, this one I don't. And f of A has to be f of B. If f of A does not equal f of B, it's not Rolle's. It's just a plain old mean value theorem, which is fine, works for me. Then there exists at least one number C on the interval between A and B, which the f prime of C is 0. So if you look at these 3 pictures, A is here, B is here, f of A is here, also f of B is the same height. So the first thing we check, is it continuous on the closed? From A to B. This point here is part of the function. It starts here, and then I have to jump up here to go down the rest of it. It's not continuous on the closed. There's a big jump. Look at this second picture. Here's A, here's B. F of A does equal F of B. And let's see. Is it continuous on the whole interval? Let's see. Climb, 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 climb. Oh, fall down. Climb, climb down, climb down. Not continuous on the closed again. Okay? So we lost it because of the hole that's in the middle here. Third one. Here's A, here's B, here's F of A equal to f of b. Okay, fine. Slope is 0. That's fine. Is it continuous from A? I didn't jump. I didn't fall. Yes, it's continuous. Continuous? Yes. Is it differentiable? We just got done doing a problem. Is this differentiable everywhere on the inside?
No.
No, there's a cusp. So it's not differentiable on the open. So we can't use Rolle's theorem on this one either. You can't even use mean value theorem, because both mean value theorem ask for the same thing, the differentiability and the continuity. So that's just an example of where those mean value theorems or Rolle's theorem fails. Then his example 1 is out of the blue. I don't even know why he threw this in there. He's asking us to show that this function has a real zero. In other words, that this function does cross the x-axis somewhere. He didn't say find it. He said, does it have it? And I'm going to show you a way to approach it without cheating. Don't use your calculator. Okay? If I just want to make a table, f of x, okay, well, not that. I don't want to do that. I want to make a table, x and y. X's and y's. And I start with like a -2 and just plug it in. And if I get it wrong, you better stop me. -2 cubed is a -8, because that's a -2, -2, -2. -2 times 3 is a -6, plus the 1. That turns into a -14 plus -13. Okay. Then I'm going to go down the list, do a -1. Let's see what that looks like. -1. -1 cubed is still a -1. -1 times 3 is a -3, plus 1. That looks to me like a -3. Okay, try a 0. 0 cubed plus 3 0, that's still 0, plus 1 is a 1. Okay, I maintain I'm done. I can stop. I just proved it. There's a 0. How do I know? This number is negative. This number is positive. How do you go from down here, from negative to positive, unless you cross the x-axis? Now, to me, that was not Rolle's theorem. That was not mean value theorem. What theorem was that? Don't let second period make you look bad. Somebody in there knew the answer. What theorem was this? We've had this already.
Wasn't it the extreme value theorem?
The extreme value theorem looks for max and mins. The one you just had.
Wait, sir, I don't know. I'm just gonna guess, but is it the squeeze value theorem?
There's nothing being squeezed.
Okay.
Squeeze theorem is where you have a maximum and a minimum, and there has to exist something in the middle. And if you squeeze it together like bread with a bologna sandwich, then you can kind of compress them together and say that the bread is touching the meat in the same place as the other bread is touching the meat. Keep going. I'll give you a clue.
The I theorem.
The I theorem. The I theorem? Where did you study that one?
Okay, sorry if I get this wrong again. Is it the intermediate value theorem?
Bingo.
I meant that one.
That's what you meant, right? The I theorem. IV theorem. Intermediate value theorem talks about the in-between. Remember? I called it the in-between theorem. So in between a negative and a positive must be a 0. Okay? But if you look at his solution, it's kind of funny. He does the same thing I did. Okay? he does the same thing as I did, and he even calls it the intermediate value theorem. And then he tries making a stretch and try relating it to the Rolle's theorem. It's crazy. He says, now, if there were even 2 points, x equals a and x of b, where f of x is 0, was 0, then Rolle's theorem would guarantee the existence of a point x equals c between them where f prime was 0. I just don't see it. I mean, I'm not sure where he's going with it. I didn't like it. Didn't like it at all. Okay. Then he starts doing the theorem about the mean value theorem. Okay, and he does mention that it was first stated by Lagrange, and I don't think Lagrange is really that famous for the mean value theorem. Lagrange is actually famous for some things that are very high level mathematics. But anyway, you see how you have this blue function, nice and pretty. It's smooth and it's continuous, and we're only going from A to B, so therefore at A it exists and at B the point exists. So Lagrange said that if this function is continuous from A to B, including A to B, and it's differentiable everywhere in between, then there must exist a tangent line on that function that has the same slope as the secant between the 2 points. So there's the slope of the secant, and there's the slope of the secant being set to f prime of c. We're looking for that c, the x value that is between a and b. It's an x value that's we call c between a and b. Okay, so it has to exist. At least one. Okay, so let's see. He shows you a picture of a semicircle, and we're going from -1 to 1. And the only reason why he shows this picture in the book is he wants to let you know that this is a semicircle. Y equals the square root of 1 minus x squared is the top part of a semicircle because he doesn't have a negative there, so it's a positive. And if I square both sides, y squared equals to 1 minus x squared, and then put the x squared on the other side, x squared plus y squared is 1. So it's a semicircle. With the circle would have been centered at 0, 0, and the radius is the square root of 1, which is 1. Well, there it is. 1, 1, 1. And he said, look how it's not differentiable on the endpoints. It's not differentiable because on a circle, the top and bottom are horizontal tangents, but the left and right side, they're vertical. So he's just showing you that even though it's not differentiable at the endpoint, mean value theorem, or in this case, Rolle's theorem, because the secant is a slope is 0, therefore there has to be a tangent that has slope of 0 as well. So it is an example of the mean value theorem, but this also is Rolle's theorem because its slope is 0. That's in the book. Here's your first problem that really talks about the mean value theorem. The function is y equals x squared. And you know what y equals x squared? It's this beautiful parabola that opens up and goes up on both sides forever. He gives me an interval from 0 to 2. So that's why we're starting here and ending here at 2. We're only talking about this part of the quadratic. So my first question, you always have to stop and ask yourself, if you're doing the mean value theorem, from 0 to 2, closed interval, is it continuous? Yes or no, guys?
Yes.
It is. Then you have to ask yourself, on the open from 0 to 2, We don't care about closed now. Is it differentiable? Can I take the derivative everywhere from 0 to 2, not counting 0 and 2? Is there a tangent line here? 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 Yes or no?
Yes.
Yes. So then, mean value theorem apply. Well, let me ask you this though. Does f of a equal to f of b? This height here, is it the same as this height here?
No.
No. No. So it's not Rolle's theorem, okay? It's not Rolle's theorem, but it is mean value theorem, okay? Not a big deal. Not a big deal. It's not a deal breaker, okay? So now I got to find the slope between these 2 points. Now the points were 0, 0, and it looked to me like 2, 4. You agree? So I'm going to find the slope because it's going to be f of 2 minus f of 0 over 2 minus 0 will have to equal some derivative of some c. Okay? So f of 2 is 4. F of 0 is 2. 2 minus 0 still has to equal f prime of some c. What's 4 minus 2? 2. What's 2 minus 0? 4 equals f prime at some c. What's 2 over 4?
Wait, sir, how did you get 2 from f of 0?
I don't know. I lied. Took you
Because
guys a
I thought we were doing x squared.
Yeah, when x is 2, it's a 4, isn't it?
Well, but
Yeah.
then it's the f of 0.
Is 0.
You put 2.
No, this
Wait,
was
what?
this x here, and this is another x. This is one of the y's, the other y. That's the x. That's the other x.
Oh, okay. I get it now. I thought, okay. Never mind.
Okay, so I'm left now with 1/2 equals 2, the derivative with some c. So since you told me we're dealing with x squared, what is the derivative of x squared?
2x.
Did anybody say it?
It's 2x, sir.
It's 2x. But I don't care about the x. I'm going to put 2c instead. How's that? Because some c is an x value, so I'm going to put a c here. So when I solve that, if I did it right, and I don't remember that answer. And Mackenzie would have told me already, I think. Yeah, I think Mackenzie would have told me if I had.
Wait, no,
Wait a minute, I did do something wrong.
because it's 4 minus 2. That's 2 over
Yeah,
2.
yeah. So what's wrong? Tell me what's wrong.
Well, it's supposed to be 1.
4 minus 0, isn't it?
Yeah, that's what I was
Oh, okay.
that's what I was talking about the first time, but
Oh, okay. It just, okay. When I said one y and the other y, I even wrote f of 0, but why did I write down a 2? I wrote it correctly here, and I didn't. Okay. There, that's it. So let me do that again. It's a 4 over a 4, which is what? Not a half. It's a, what's 4 over 4?
wait, sir,
Yes.
doing it correctly? Because you
It's
said
not 4 over 4. It's 4 over what?
2.
2.
Because it's 2 minus 0. Okay,
So what's 4 over 2 then?
that's 2.
2. Okay. Then what's c then?
1.
Yeah. Okay. I remember that answer. C is 1. I mean, you could actually see it here. That somewhere between 0 and 2, this tangent line, this yellow line, can just slide straight down without changing the slope. And right around here it's going to be a tangent line is the same slope as that yellow line. That slope is 1 as well. Thank you, Hector. Yeah, so you gotta keep me honest. You're the only one that sensed something was wrong in the force. Your spidey senses was tingling, and even I couldn't put my thumb on what you were talking about, but eventually I was seeing that's not right. I saw the answer before. I did it the other day, or I did it this morning. Okay, now this was a way to use the mean value theorem in a sense. When we talk about f of b minus f of a over b minus a, that's the slope formula, right? And the slope formula means it isn't a surprise to say that you could use this idea of the slope of a secant line to talk about what's happening in the middle. Here's what's happening. Well, by the way, if we say that the slope is equal to f prime, then what we're saying is the average rate of change somewhere is equal to the instantaneous rate of change. This is instantaneous, this is average. Somewhere in the middle, they're the same. Okay? Here's an example. If you're driving a car, and let's say you're driving a car from point A to point B, and let's say that's 100 miles distance, 100 miles. And as you're driving, you know that there's a police car up here waiting for you. So when you pass that police car, you are going 55 miles per hour. Mr. Honest Abe, you're not speeding. You're a good boy or girl. You're not going to speed. So you pass it, and that police officer says, oh, what a good guy. And then, an hour later, police car B puts the radar on you, and guess what? You're so good, you're going 55 miles per hour. Should you get a ticket? What do you think?
No, because that's impressive.
It's impressive?
Wait, are they going 55 miles the whole time?
No, of course not.
Oh, okay. I
How
thought
can you get?
I
How
was
can you
like,
get
that's
100
pretty
miles?
impressive.
That would be. Yeah, he had to. Yeah, he had to use like teleportation. It's only an hour later. So what you don't know is that in some places they have a camera that take pictures of every car going by this spot and every car going by this spot, and a supercomputer is connecting those two pictures and saying, "Hey, wait a minute. What's his average rate of speed? It's not 55. He was doing 55 here and 55 here. How did he go 100 miles? Somewhere he had to speed up, didn't he? Somewhere he had to speed up, and he was speeding somewhere. I don't know where he was speeding, but he was speeding. Okay? So here's an example of how you can actually talk about it. If you're doing in 8 seconds, you're traveling 352 feet. You can actually calculate what your average speed was. It's only 8 seconds, guys. Who knows how fast you were going in 8 seconds? Here's 0 seconds. Here's 8 seconds. But you can calculate the average speed because at 0, you were doing 0 speed. And at 8 seconds, all you know is you went 252 feet. So you went 0 distance, now you're at 352. So what we can do here is calculate our speed. 352 feet per second is the same thing as the slope, because it's y2 minus y1 over x2 minus x1. Y2 was 352 minus the 0 over 8 minus 0. How fast is that? What is 352 divided by 8?
44.
44 feet per second. Okay, physics people. 44 feet per second. How many miles per hour is that? Well, I thought somebody would have got it.
Wait, sir. Let me get my calculator.
No, you don't have it memorized? We used to have this one memorized.
Oh.
But, okay, you don't need a calculator. Well, you will need it in a minute. Let's just do it with what you, since we don't know. 44 feet per second. Let's get rid of seconds. Multiply by 3,600 seconds per 1 hour. And let's get rid of feet. Let's multiply, how many feet are in a mile? Isn't it 5280?
52.8. Oh, okay.
So what happens? Oh, that's 5280. I got it the wrong way. I need to switch it around. Switch.
Wait, sir. Wouldn't the
Mile. Yeah, no, mile got to go on top.
Okay, yeah.
5280 feet goes down here. 80 feet goes here. What happens is the feet cancel out, the seconds cancel out. Oh, now use your calculator. 44 times 3,600 divided by 5280. Mr. Calculator. You're still typing?
I got 30.
30 miles per hour. The number that I learned in high school was 88 feet per second is 60 miles per hour. Because when I was young, 60 miles per hour was pretty much a speed limit everywhere, on every highway. You didn't have 70, you didn't have 65. There's a big saying, 55 saves lives. That's really what they wanted to do, is 55. I remember when every highway was 55 miles per hour. You would have to drive to San Antonio from Harlingen at 55 miles per hour. You could not ever go 60. You could get a speeding ticket. So anyway, you know what's happening here. You got this, you're traveling. Is this the same problem? Yeah. You're traveling, and the slope is your average speed. That doesn't mean you are always going 30 miles per hour. It's just an average speed that you are going. You could be going slow, you could stop, you could speed up, but on the average. All right, here are a couple corollaries that I really don't know how they're fitting this into mean value theorem, but I'll cover it. If f of x is 0, f prime of x is 0, it means your derivative is 0 at each point on an interval. So here's your interval. You're going from A to B. And if you say everywhere you go, the slope is 0, well, that's not this picture, because look at, that's not 0. That might be 0. That's not 0. That might be 0. That's not 0. What would that shape have to be to go from A to B to have the slope always be 0? What kind of line is this?
Horizontal line.
Horizontal. So he says to you, if your derivative is 0 everywhere, then from A to B, your function must be a constant. Y equals to 2. Y equals to negative 5. It's a constant. And then another one he says here, if f of x equals g of if your derivatives are the same, if f prime equals g prime, does that mean f has to equal to g? Does that mean your functions are the same? Well, it's not, because just because the derivative is always the same at every single x, one function could be different by a constant. If y equals to 3x, y prime is 3. If y equals to 3x plus 2, y prime is still a 3. You see that? If y equals to 3x minus 10, guess what? Y prime still is a 3. So a function could be the same derivative everywhere, but the function could be off just by a constant. That all the constants, this could be plus 0, so that constant is 0. So the problem he gives us, well, here's an example. Here's a whole bunch of parabolas. They're all the same parabola except some are shifted. Like y equals to x squared. That's this one right here. That's the red one. Or y equals to x squared plus 2. That's this one up here. Or y equals to x squared minus 1. That one is this one right here. If you take an x value, whatever x sub I, it has a slope. You go up, it has the same slope. You go up, has the same slope. You go up, it has the same slope. Because the constant, when you do the derivative, it goes to 0 anyway. So his problem here is, let me go to the next page, so you can't cheat.
Well, sir, can't you say that if an equation has f of a equal to f of b, then the slope would be 0?
Yes.
So separating it would be the constant.
Yep.
Okay.
That's what he was saying in corollary 1, basically. Yeah, exactly. But don't look at the answer. I switched the slide. I don't know how I did that. Find the function f of x whose derivative is sine. Derivative of something has to be sine. You want to take a guess? Has to be a trig. What is the derivative of sine, by the way? Derivative of sine. Somebody.
Cosine.
Cosine.
Is. What's the derivative of cosine?
Negative
Sine.
Oh, negative sine. Well, then what would I put here just to get a positive sign?
negative cos.
You're good.
8, let's go.
You're good, man. Negative cosine of x. That's right. Now, what he wants you to realize is that's true. But remember, it's not always just cos, because you could have put negative cosine of x plus 1 will give you the same derivative, won't it? Or the derivative with respect to x of a negative cosine of x minus pi, wouldn't that give you the same derivative? Yes.
Yeah.
So what you want to say is this. Your answer should have been, my f of x should have been negative cosine of x plus some constant. Whenever you're looking for the function that has a derivative of something, and you come up with the function, always say plus a constant. It could be a negative pi, it could be a negative pi over 2, it could be plus 100. It doesn't matter, because when you take the derivative from left to right, that always goes to 0. All right, what's next? Something, I don't know why he has this in the chapter. E is a number, 2.7 something, okay? But who cares? If it's a base of an exponential, like e to the x is an exponential growth, if you have e to the x times e to the another x of something, could be any x's, could be a 2, could be a 4. To put those together, you add the exponents. And when you're dividing, where's that one at? That's this one right here. You have two bases that are the same with different exponents, you subtract the exponents. And the second one, he had that negative power, to make it positive, it has to be shoved downstairs and you make it positive. And then if you have a power to a power, you multiply those powers. And if you want to be really silly, that was e to the x1 raised to this. That's the same thing as e to the x2 raised to x1 because it doesn't matter which order these power to a powers are. I don't know why that was part of our lesson on mean value theorem, and that's the whole lesson. We have 5-6 minutes left. We can do a problem that you have in the textbook here. Pick one.